Yeah, hi everyone. This is the session about advanced Katib features. I will start with sharing my screen. Okay, can you see my screen? Okay, I guess so. Just to give you a quick introduction again. So I'm Andrey. I'm a software engineer in Cisco. I used to work in Kubeflow from 2018. So almost 3 years already. And I'm working with AutoML and training working group. And especially I'm building the neural architecture search platform for Katib. I'm helping community to grow CI/CD infrastructure, distributed training operators, and all of the release infrastructure work there. And here we were talking about like advanced Katib features, which we kindly touched in this summit before, but we will speak more about. We will show like a couple of demos, how they can use it, and we will also see how to perform different experiments and examples there. Yeah, so the first thing that I want to discuss about early stopping, and especially how to use early stopping in Katib. So what is early stopping in general? This is the common hyperparameter tuning techniques, and early stopping is used to avoid overfitting for your model. So imagine that you have thousands or 10,000 of trials, which all running in parallel, and all of these trials are running the same model. So eventually, you don't want to actually train the model from start to end if the model just produce batch results. For example, in your model, you can have like the bad accuracy, but you don't want to actually collect the metrics from the accuracy, which is much, much worse than the sum value. And we actually support early stopping in Katib, and which is more important, we support it with super easy way from our user perspective. So to use our early stopping currently, you don't need to do anything else from your training code perspective. So you can use the same examples as I used before with the same printing metrics that you used before. So we use the same metrics collector. And so what you need to do, you just need to simply extend your YAML with the early stopping parameters. And as the same as the algorithm you specified, you just need to specify the algorithm name and the algorithm settings. And in the meantime, currently we support only std out metrics collector for early stopping because we're analyzing the metrics from the output that I will show you later in the demo. These techniques is very useful because it, as I said before, it helps you to save a lot of computation resources. It helps you to save your memory, your GPU, your GPU resources. By the way, in the meantime, I just forgot to mention, if you have any questions, please feel free to ask me during my session. We have like around 1 hour, and the features that I will talk about in this session are a bit sophisticated. So if you have any questions during my session, please feel free to interrupt me. Yeah, do you have any questions about early stopping? We can move forward. Okay, sounds great. So the next thing that I really want to talk about the customer source. So currently in Katib, we support, we dynamically support any type of the Kubernetes resources. So in the upstream, currently we support TEJob, PyTorchJob, MPIJob, and Tecton pipeline. So as I mentioned previously, in Katib can be orchestrator on top of your trial template. So trial template can be a simple Kubernetes job, but in the meantime, trial template can be sophisticated Tecton pipeline with the pre-processing data, your data set, and also some sophisticated process that you can do during your hyperparameter tuning optimization. So if you have your Kubernetes custom resource, you can easily integrate it in Katib as long as your Kubernetes resource create Kubernetes pods, allows Katib controller inject sidecar container for the metrics collector, and in the meantime has the succeeded and failed status. So almost all of the Kubernetes resources following the same way, and if they can be integrated in Katib, you can do it very easily. So you can just need to follow 2 steps. So the first one, just updating the controller arguments with your customer resource definition. So this is the like the group version kind of your resource. And in the meantime, you need to update the Katib controller cluster roles to be able to provide access to your resources. So in this particular example for Tecton pipeline, Katib will create the pipeline runs, the task runs, and that is why we need to give the permission to allow Katib controller interact with these resources. Yep, and or even more, as I said previously, you can integrate your custom internal framework in Katib. For example, you have your own Kubernetes customer source, which is not shared globally, but you can use Katib internally and just extend this functionality by using our image and just use your internal customer source definition. Yeah, any questions? Okay, sounds great. Yeah, so we will also show, I will show the demo with this customer source, and I will show how to perform Tecton pipeline in Katib experiment. Yep, so yeah, go ahead.
This is Charles. You said we can trigger a Kubeflow pipeline from the Katib template.
Yep.
Can you shed some more light on that? Do you have an example later on that you can demo?
Yeah, so this is a very interesting question because I know that we actually contributed in this integration, and the guys from Kale, they integrated the Kubeflow pipelines as the job. So eventually they use the Kubernetes job to run the Kubeflow pipeline. Currently, we don't have this example in upstream, but we, as we said before, we will create an issue and we will try to actually show this example particular in upstream Katib. Because Kubeflow pipeline is just a simple orchestrator, and as long as we can even like put the Kubeflow pipeline in a trial template, we can use it in Katib. But we definitely want to support it in upstream with a particular example.
All right, thank you.
Yes, so moving forward to how to actually use the custom trial template in your Katib experiment YAML. So the 4 parameters that you need to set up, the first one is primary port labels. So why do we need to set up these parameters? Because the metrics collector needs to know which port needs to be injected and which actually container needs to be wrapped. Because metrics collector, I actually use some internal functionalities to be able to collect the metrics from the training code. And in the meantime, we need to provide these parameters to our controller. So just the 4 simple parameters about primary port labels, which is specified which labels your training container pod has. In case of TEJob, our main training container will have like master label. And you also need to specify the primary container name, which is eventually your container, which is running your hyperparameter tuning job. So in this example, we have like TensorFlow primary container name. And here you can see like the container name is the same. So because imagine you definitely could have like more than one container in your TEJob YAML. And you could have like some other like Istio proxy or any other containers that you don't really want to be wrapped by our metrics collector. And also we have success and failure condition, which is specified a particular condition in succeeded or failed status during the customer source run. All of these parameters in the upstream custom resources is done by default. So our users just don't see these parameters for the simple experiment. But if you want to run your custom experiment, you definitely need to specify these parameters. Yeah, I think we can move forward. Yeah, and the next thing that I want to discuss about landscape of AutoML, because eventually we want to build Katib as the cloud native AutoML framework on top of Kubernetes. So in our ideal world, we want to support all of the AutoML features in a Katib project, such as feature engineering, model compression, neural architecture search, hyperparameter tuning, and currently in the landscape of AutoML, you can see that you have your training data, which is pushed to your configuration space. And here you have a different sort of the optimizers. So imagine you can optimize not only your architecture, not only your hyperparameters, but also architecture, where we will see in the demo how does it look like. Because in hyperparameter, you're just searching for the particular parameters. But for NAS, you're searching for the whole model. And in the meantime, this optimizer can be done in different ways in such a different optimizations problems, not only for the hyperparameter tuning job. Also, like we can touching like feature engineering, which is completely another sort of the discussion, but also can be part of the AutoML. And in the meantime, all of this data can be pushed to your production model and can be produce just very good predictions. And if we're speaking about like neural architecture search, because we will be specific to this field in the next slides, in a neural architecture search, in the ideal situation, you can just provide us like the project data set, and then we will give you the state-of-the-art model. So all of these functionalities can be done out of the box, and this is the goal that we really want to achieve doing the neural architecture search. So speaking about neural architecture search, as I said, this is the process of searching the best models, the best architecture for your models. And I think back in 2019, there were a lot of really good papers, which kind of algorithms NAS can support and which kind of algorithms we can perform. So a couple of algorithms using reinforcement learning techniques, which is basically has two different things: the RNN controller and the child network. And we will see this in our particular example because one of the algorithms is using these reinforcement learning techniques. And in reinforcement learning techniques, the RNN controller produces the architecture with some sort of the architecture that we provide to the trial, because you can think of training the process in the one particular trial. And we just try to train this network and just to get our final accuracy or the final reward. And we just send this reward back to our RNN controller, and our RNN controller train independently and produce a new architecture. So eventually this process repeated again and again and again. If you have like, I don't know, a couple of days and thousands of GPUs, this is a very good algorithm which produce very good results for you. But if we go forward with some other implementation, which is like efficient neural architecture search, this is one of the implementation of using like this RNN controller, but with a more modern way. And we're trying to actually achieve this algorithm in Katib. So what is kind of different between simple reinforcement learning techniques and ENAS? Especially in ENAS, as I said before, they're using the same RNN controller. But in the meantime, they trying to share resources and share weights across different parameters. So basically, they're trying to compute this graph, combining all of the possible operations, and then they're trying to see what is the best way to connect this operation. So basically, this graph, we will definitely see all of this in the demo. I will just show you later in the demo. But eventually, they share their weights from your training, from your architecture to the RNN controller, and to see what is the best parameters produce the best results. So in this particular example, here you can see the architecture. Which here we use the CNN, so convolution neural network, and it has a couple of layers. So in the first layer we have like convolution with 3x3 filter size, and then we have like separable convolution, and this is mean skip connections, which we also see in the demo more particularly. I will not go deeply how does it work in the math perspective, because there are some sophisticated and complicated problem. But if you want to learn more about ENAS, definitely I would strongly recommend to just go to this paper and read more information about this ENAS implementation. Yeah, and speaking about other algorithms which NAS can provide, there are like a couple of them. And one of them, which is like very interesting, which is called differentiable architecture search, DARTS in short. And eventually, it is not using RNN controller. It is not using reinforcement learning. All of the training process is happening in the one trial. Because previously, as I said, we could have different architecture, and this architecture needs to be trained from start to end, and this architecture need to share the parameters. So this process is very time consuming. But what happening in DARTS? In DARTS, they're eventually trying to construct the combination of a different operation for the particular cell. So a neural network is just a combination of the different cells. And in this picture, you can see just one cell. And they're using the continuous relaxation to be able to see what is the actually best operation needs to be from one operation to another. So this maybe sounds very confusing, but overall, we're trying to share the weights from your training model to these alphas, and we will also see this in the demo. How does it actually work? But overall, it has like separate controller to train this sort of the graph, and based on these weights, it just produced the best parameters for your architecture. So eventually, for darts, I know that they're using sort of the macro and micro search, which is a completely different strategy. In the micro search, you're searching for the particular cell, but in macro search, you're searching for the particular neural network. So if you're searching for the particular cell, this is the process. How does it look like? So they're trying to they're trying to share the weights from the training process to this method to be able to generate the best operation parameters for your architecture. Yeah, and speaking about like darts again, as I mentioned, they have like a normal cells and reduction cells, which is different, which is actually located in reduction cells located in this part of the neural network depth, and the normal cells located on the other side of the of your depth. So basically, and also like this is some settings from the paper. And again, if you want to read more about it, I strongly recommend just follow this paper to read more about darts. But overall, this is the structure for the particular cell. How does it look like? And by using the cells, the data scientists can construct the full architecture for their model. Yeah. So any questions to darts or ENAS before we jump to the demo? I know that it maybe sounds confusing, but still. Okay, sounds great. I think it maybe will be more questions to the demo side. Yeah, and I just want to show how we actually deal with a NAS specification in Katib YAML. So eventually we specify the NAS config where you have your graph config. So this is just the specification where you set like number of layers, you set your input sizes. So this is the example for CNN for CFAR10 dataset where you have like the images with this resolution, and you have 10 different images as the output. So this API is very early, and we really want to hear the feedback, what our users think, how we can improve it, and so what is the best way of doing this API. And the search space, how we currently describing the search space in NAS, we specifying the different operations, and each operation has their hyperparameters. So this is like similar to hyperparameter tuning, but more in architecture point of view. And imagine that your neural network can have n number of convolution layers and number of reduction layers, and all of this search space you need to specify in the operation stack. Yeah, and other parameters are the same on the experiment way. Okay, so before we jump to the demo, any questions to NAS or to other techniques? Okay, sounds great. Let's jump to the demo. Yeah, so for the demo, I think we will see a couple of examples. I think I will show 4 particular examples: early topic, tecton pipeline, ENAS, and darts. Yeah, let me first of all copy these examples to our dashboard. I will first of all just submit an ENAS example because it takes some time to be completed. And in the meantime, I will just pause the early stopping experiment. So first of all, if we jump back to early stopping, as I said before, this is the particular example where we use just a simple random algorithm. And for the early stopping rule, we're using the median stop, which I will discuss later how does it work. And we just defined some algorithm settings for this median stopping rule. And the other parameters are the same. So we're using 15 trials, we train 2 trials in parallel, we tune learning rate and number of epochs. On demand, I just produce very bad results for learning rate to see which trials will be early stopped. And we're using just a Kubernetes batch job to be able to see, to be able to perform the training job. So eventually, if we jump to our console, by the way, can you see my console?
Yes.
Okay, sounds great. Yeah, so let me first of all, So I think if you attend the Jonas session before, he just explained what does it mean, like experiment, suggestion, trial. I will not just explain this again. If you're just interested in it more, I strongly recommend to see the session about Katib user journey. So if we just try to see what's happening in our suggestion. So in case of early stopping, our suggestion pod has two different containers. So the first container is the suggestion container, which just produced just a trials, so the same way. And the second container is the early stopping. So let's try to see the logs from them. So what is the median stopping rule, first of all? So the median stopping rule is just the sort of the early stopping algorithm, which actually stop the trial at the particular step. In our particular example, at step 5. When I'm speaking about the step, imagine this is just an epoch. So stop and epoch number 5. And if the trial objective metric is worse than the median value, we just simply stop this trial from our execution. And because of that, we save a lot of computation resources. So we specify two parameters. So the first one is minimum trials required. We definitely need to collect, first of all, before making the making this prediction, making this before stopping the trials, we need to collect some data, right? And we, first of all, we collect data from 3 trials and wait until 3 trials will be finished. So this is the first trial with the first accuracy, and we collecting this accuracy. So this is the second trial, which has very bad accuracy, but we're still collecting this accuracy. And this is the third one. And once we collecting the third trial, we producing the new error stopping rule, which means all of the trials after this step will be stopped if the accuracy is less than this value. So this value is just the median value for all of these 3 trials. And this is the early stopping rule. And even more, if we try to describe one of our trials, yeah, for example, let's take on this one. Yeah, if you try to describe the trial, you will see the particular early stopping rule here. So this early stopping rule, we're sending this early stopping rule to all of the trials which are happening after that. And in our particular example, you can see that this median stopping rule will be modified because a new trial just completes, and we need to adopt this validation accuracy parameter. Yeah, and also if we try to actually see our training process, yeah, for example, let me take a look. Yeah, let me first of all see what of the trials was succeeded. So as we can see, only one trial in our case was early stopped, and this trial was succeeded. So we're also updating the trial status, which was actually which were early stopped. And if we try to take a look of the logs of the trial number 49, so this is, I think, this training container. Yeah, so as we can see here, this is just a training process. This is just a simple toy MNIST example. But overall, as I said before, the training process will continue until we reach the particular epoch. So in our case, until we reach the epoch 4, is just compare the accuracy value with our early stopping rule. And since this value is pretty bad, then we just early stop trial. And under the hood, we killed our main training process, and we changed the trial status. So imagine if you have like thousands of epochs, you will not, and all of the trials are using GPU, you will not actually, this GPU will not be acquired by some trials. So you can just simply improve your efficiency of the using resources. Yes, and in the meantime, if we try to take a look at the other logs, in, for example, from this one. Yeah, so in the this trial was completely finished from the start to end, and as you can see, after the epoch number 4, we haven't like stopped this trial, and we have like the final results. And even more, if we go to our UI, this is unfortunately the old UI, because we are working in the meantime with Kamonos to integrate these features in the new UI with the early stopping implementation. Yep, and in the UI, you also can see the statuses of our trials. So some of them was succeeded, some of them was early stopped, and so which is more important, if you click to the trial, you will see that for the succeeded trials, we reported like 1, 2, 3, 4, 5, 6, 7, 8. So particular at 8 epochs, so from start to end. And if we click to early stop trials, we have only 1, 2, 3, 4, 5 metrics, because we comparing the value on the step number 5. And this is happening for all of the other trials. Yes, and if we start, we will see like the trials with the best validation accuracy will be succeeded, and the trials with the not really good validation accuracy will be early stops. Yeah, I think, do you have any questions to the early stopping, or we can jump to the next example? Okay, yeah, go ahead. Okay, sounds good. Just you can also like use the chats in the Zoom if you have any questions, and we can answer them after that. Okay, so let's jump to the next example, which is Tecton pipeline example. And for that, let me first of all copy. Yeah, I will copy example from here to our dashboard. Okay. Yeah, first of all, let me just briefly introduce what is it. So Tecton pipeline is similar to Argo workflow. So just a similar pipeline orchestrator on top of the Kubernetes, where you can use any sophisticated pipeline that you want. So if you're just familiar with Kubeflow pipelines is using Argo workflow is the default backend. But in the meantime, we have in Kubeflow, we have the KFP Tecton project, which is using Tecton as the orchestrator. So in this particular example, we are using Tecton pipeline as our trial template. And as I said before, previously, I will not go deeply to the other parts of the example. Just we will use random algorithm. We will use like 4 trials, 2 trials in parallel, and all of the parameters are pretty similar. Only thing which is interesting about the trial template. So in trial template, as I said previously in the presentation, you need to specify the primary pod labels, which is eventually your particular pod, which are running, which is running the training, which is running like training code. In this particular example, we have our Tecton pipeline with two steps. So the one step is pre-processing, and the second step is the actual training. And here we're specifying the primary pod labels, we're specifying the primary container name, and we also specify the success and failure condition for our Tecton customer source. So speaking about like this pipeline run, as I said, this is very good that you can see like the whole YAML structure without any string changes, and even more in Katib SDK, you can just define this trial spec as the JSON format, and you can easily parse it if you want to. So this is a very good way of just showing this template in the trial spec. So in the pipeline run, what we're actually using, as I said before, we have like 2 different steps. So the first step is data preprocessing, and the second step is model training. So in data preprocessing step, what we do have, so we have number of examples, which is initially 60,000, and we just want to randomly divide this number by the random value from 10 to 100. Imagine that you have any sophisticated preprocessing here. You can just have your preprocessing data set. You can share the PVC, so you can use all of the functionality from the Tecton or from Argo in Katib in general. So, but this is just for an example. For example, we just simply divide our number of examples by random value. And then in our model training step, we just have one parameter, which is learning rate. And this parameter we're trying to tune. And the second parameter is the number of examples that we achieved from the previous step. So as we can see here. And then we're just passing these 2 parameters to our model training step. And we're using the, again, MNIST example to train these parameters. Yes, so let's try to submit this example as well. By the way, the Tecton integration is already in upstream, so you don't need to do anything. I just want to suggest if you want to see how does the Tecton integration works in Katib, please feel free to check this tutorial section here in the Katib examples. But overall, yes, we created our experiment, and we can go back to our terminal. And again, as I said, so imagine that currently each trial is a Tecton pipeline, which has two different steps: model preprocessing and model training. And if we, for example, take one of the trials, so if we take this one, like VX5, so as we can see, it creates, it creates two. Let me actually again check a look at the pods. So first of all, let me actually describe this trial to see how does it look like. So in the trial you have the same template as I just explained previously, but the particular learning rate that our random algorithm produce. And if we try to take a look in our pods, so we're using this particular trial, and this particular trial is having the data preprocessing pod and the model training pod. So the data preprocessing pod has like 759 value, which is eventually just a random value which we generate, and we just passing these parameters to our model training steps, which we hope we can find it here. So I just currently trying to see the logs from our training container, and as the input parameters, it should be right here. So we're just passing these parameters to our training step. We're also passing the learning rate, and we started to do training process, and we also like report all of the metrics to our Katib DB. And even more, which is very interesting, that because we're using Tekton, we can use the Tekton dashboard, which is completely independent project or not in the Kubeflow organization. But since it supports the viewing of the current pipeline, you can see what is the pipeline runs, or what is the logs from these steps. You can see the different statuses, details. You can see what is the current tasks are running, what task has been succeeded. So all of the functionalities that Tekton community provides definitely can be supported. And you can analyze these results very easily. And even more, again, if you go to the Katib dashboard, and if you click to the Tekton pipeline, you will see that all of the trials has been succeeded. We successfully collected the validation accuracy, train accuracy, some learning rates that our random algorithm produced, and we also like collect our metrics results from our training container. So again, this can be done with integration. We continue to work with integration with Argo CD and Argo workflows to be able to run not only Tekton but also Argo, and this can be increased in tremendous way. So, do you have any questions regarding to Tekton or Aristomic, or we can move forward to our NAS examples? Okay, sounds great. Yes. So let me actually introduce two latest examples for the NAS. So we already submitted the first experiment, which is used ENAS algorithm, which I described before. And first of all, let's just take a look at the experiment YAML that I submitted. So in our experiment YAML, we have the same graph config. I think I'm not using like this number of layers because, but this is just similar. I just try to decrease the parameters to make sure that we will finish this process fastly. And we also like specified this graph config that I explained in the presentation. We specified this sort of the different operations, which is like convolutions, which is separable convolutions, so like a search space for your architecture. And we also like define the trial specification for our ENAS algorithm. In the meantime, let me actually submit another Dart example because it also will take some time to be able to submit it. I think our ENAS example already finished, so I will just submit another Dart example, and I will just explain how ENAS is working in Katib. So if we go back to our terminal, and first of all, I just want to see the logs from the ENAS suggestion. So we currently, unfortunately, we're currently following for NAS because NAS is completely different with the hyperparameter tuning, but we're still following the same way with the suggestion, with the trials, and with the experiment as we described before. So we have our suggestion, and in our suggestion, we actually running our ENAS algorithm. Let me check the logs. So as I said, ENAS under the hood using reinforcement learning techniques and RNN controller to train internal model to be able to produce architecture. So first of all, what do we need to generate? We need to generate the combinations of all operations. So each operation will have their own unique ID. So because our controller needs to know how to construct the model, we need to define the set of the different operations, and we're just parsing this set in our RNN controller. So we have a couple of settings for our RNN controller. And first of all, our RNN controller produced the first architecture. So this is very important. I just want to explain how the architecture looks like. But as you can see here, this is the model. This is our model that our training container received. And how does that model look like? Because this is not a model, right? It's not like the model in PB format. We're just passing the model in string format. So, so this is the architecture of the model. And what does 81 means? Our trial pod will understand what is 81 means, because we also send the corresponding search space description. So 81 means separable convolution. And so what does 6 means? 6 means, let me take a look here. So 6 is just a simple convolution. So again, our child just received this information, and our child pod has like the model constructor to construct like the whole model by using these two neural network architecture and the search space description. And you might ask me, what does it mean like 1 and 0 means? It means like skip connections. And it's widely used in ENAS techniques and in some of the CNN models. So connections means that we actually parsing some information from one layer to another to produce better results. And you will see it's better too when we construct the particular graph for our model. So once we actually train this model, we also can see, we also can see like the logs from our training containers. So again, since it's using reinforcement learning techniques, we need to train each candidate after we produce the new architecture. So if we try to see, for example, logs from this trial, or sorry, from this training container as the input on the top, you will see, so here you will see the architecture that I described before, and then you will see the neural network config. And then we have like the model constructor inside our training container. And this model constructor constructs the model by using these two parameters. And then we start to train this model. We're using the CFAR dataset, as I mentioned before, and yes, this is the training process which we're actually happening. And once the training is finished, we collecting the reward, and the reward which is actually objective value, and we're sending this reward back to the suggestion to produce new candidate. So if we again take a look at the logs from the suggestion, as we can see, this is the average value from the previous trial, and we train our LSTM controller to generate new architecture based on this reward. And it's produced again the new architecture. We pass this architecture again to our training training container. It trains again, and again we have like a new result. We generate the average, and we again train our LSTM container to produce better architecture. Of course, currently, unfortunately, we do not support parameter sharing, which is mentioned before in which is used in ENAS. But we're working on this, and this is in our roadmap how we can make it cloud native. Yes, and so here in our particular example, we have 3 completely independent architecture, and even more, we can go back to our UI, and we can see how does architecture look like. So, as I said, this is the DAG, so directed acyclic graph, and data scientists can even take this graph and construct the model. Of course, we like usually receive the request that our users, they want to see they don't want to lose the pre-trained model, because actually after training container is finished, after training process is finished, we eventually just stop the trial, and you will lose the model with pre-weighted results. And we don't have the model management currently. But that is one thing that I really want to discuss with the users, how we can improve it and how we can make it better to just give the best model to our users. Because currently they can view this model, they can see that this model has like this skip connections. It model has like particular 1, 2, 3, 4 layers. And if we view the experiment, we specify so we specify particular 4 number of layers in our model. Don't be confused about this global average pooling and fully connect. This is the common use case for ENAS. So all of the ENAS algorithms, they using these 2 layers at the end. But overall, you can specify as sophisticated model as you want. You can specify more layers if your model needs to produce better results. And you can take this graph and construct the model by using this graph. Yeah. So here you can see the different accuracy that this model produces, and also you can see another model which is generated by our algorithm, and we can see the third model which is completely different. Any questions regarding to ENAS? And maybe any comments? What is the best way of representing the model for you? Okay, sounds great. Yeah. I mean, we can have a discussion after I finish it. So I have like one more example and we can have a discussion about like the model implementation. Definitely, this is very early. Again, we continually working how the API should look like, because we really want to see the NAS, which will be independent from the hyperparameter tuning. And maybe we need to use another controller and another API structure to perform this NAS experiment. But yeah, this is how like ENAS looks like. And if we jump to our Darts example. So as I said before, Darts, so Darts does not use, we don't use like, it doesn't use reinforcement learning techniques, but it still produce architecture for you. So let me first of all copy the Darts example to make sure that we have a similar example here. So yeah, so just explain what is the difference between Darts and ENAS. Again, the API is the same. Again, you need to specify your algorithm. This is some algorithm parameters. You need to specify your NAS config. We don't have like the input sizes here because currently we support only one data set. So you cannot, unfortunately, you cannot just specify any other like input sizes. But overall, you still have like the operations, different operations. You still have like the trial template, and all of these parameters are pretty much the same. But what is like more interesting if we go to the logs? Since as I said before, since Darts doesn't use reinforcement learning techniques, all of the process is happening on the one container. So if you try to check the logs from the suggestion, first of all, in the suggestion you will see that this is just produced just a search space and the algorithm settings. That's it. And we're passing these parameters to our training container. But if we try to see the logs from the training container, we will see more interesting information. So the first of all, we obtaining these parameters. We obtaining the primitive. So primitives is just a search space, and then we starting to learn to actually generate our Darts cells. So again, as I said before, in this particular example, so we're using like 3 layers. And for each layer, we have a reduction cell or normal cell. And based on these cells, we generating the different like Darts nodes. So eventually, we're using also like 4 Darts nodes as we, so similar to, I think, to this picture. So as to make it clear for you, this is 1, 2, 3, 4 Darts node. And here we have also like 4 Darts node. And we start to actually train this Darts node in the same time as our model is training. So eventually, after each epoch is finished, we shared the weight from the training process to our alphas. You can definitely read more about it in the paper, but overall, it does not require you to retrain model again and again. It will actually give you the best architecture after the first training process is finished. Yep. So in this particular example, we have like the normal alphas, reduced alphas, which is actually reproducing the normal and reduced self. And overall, this is the training process. After the training, we run validation. We share the results. We share the weights, and we generating the genotype. So just a small introduction, which is genotype. So genotype in Darts is the model architecture, and to explain how does it look like in the particular genotype. So here you can see the example, and this is, by the way, also in Katib repo. So if you're just interested, you can also like read this section about the Darts in the Katib package suggestion. Yeah, so in the genotype, you have normal cell, you have the reduce, this is the reduction cells, and basically you have the connection, you have like the particular operation for each Darts node, and you have the particular index. So this means that our actually first cell will be connected to the 0 node and first node. If you're just more interested about how does it look like, I strongly recommend to read this tutorial here to see what is the difference between indexes and basically how does it look like. But overall, in convolutional neural network in Darts, they're following the structure where they're connecting all of the nodes. That is why we have like this some sort of the concatenation. And in the meantime, in Darts, they also support not only like CNN, because we're speaking about CNN again and again, but they also support NLP models, which we also try to achieve in Katib, but this will be like the next step. But overall, this genotype is completely the same as I discussed before here. So this is just a normal cell in the more user feasible representation, and this is the reduction cell and also like a better representation. But here you can see how does it look like in the string format. Yes, so again, if we jump back to the terminal, so we start to train the model again on the next epoch, and again, we adjust our alphas for reduction and normal cells. We produced a new model genotype, which definitely should have like better accuracy, and then it shares the weights again, and it produces the new model genotype and the best genotype you can see here. So this sounds kind of crazy why they actually sharing the weights from the training model to the sort of the combination of the operation. But for some cases it works, and if you just want to learn more what is the ground under that and why they're actually doing this, again, I strongly recommend to take a look in the Darts paper. But best genotype, speaking about Katib perspective, we report this information to our experiment. So currently, if our users wants to see what is the best, what is actually the best genotype for the particular cell, they can see it. For the particular search space, they can see it here. Yep. So we're just sending this information to observation, similar to hyperparameter tuning. Yeah, so again, this is very early. I know this maybe sounds a lot of confusing, and there are a lot of questions, because in an ideal way, of course, as I said before, we really want to support, we really want to be able to hide all of these sophisticated processes from the user side, and just maybe sending the final best model as the model management part of Kubeflow. But this can be the next step. And we really want to hear what are your use cases? Like, have you tried to use NAS in your production environment? And what do you think about it? Yeah, I'm ready to answer any questions, comments.
My comment is, wow. That's incredible what you've done there, Andrey.
Yeah, because imagine, as I said, this has a lot of potential. I know that many people, they're using only hyperparameter tuning, But in AutoML world, there are a lot of things which can improve your MLOps environment. I strongly believe. The question is again how it can be done cloud natively, and this is the major question which we usually try to ask our users and to see what do they want to see in Katib and how should it look like for them. Yeah, thank you. Again, so the question is about implementation and isolating hyperparameter tuning from neural architecture search. This is our next topic. And I don't know if I have like enough time to discuss it right now, but I really want to see what to hear opinion, like maybe ideas of implementation, maybe ideas how we can name our hyperparameter tuning experiment and NAS experiment, and for feature engineering experiment, I don't know, because I think we can build a really great tool on top of the Kubernetes infrastructure by adopting all of these novel techniques, right? Okay, sounds great. Any last questions, comments? We have like 10 more minutes. Yep, sounds great. Go ahead, Aniruddha.
Yeah, it's great actually what you have shown that. But I saw a few of the challenges in the AutoML journey in my company. What I felt, right? People are more comfortable in native Python-based packages, and that was a challenge which I was also facing in my organization to make them understand what is the AutoML journey in this. I mean, the space of this, and how to use those particular tools in Katib. Now, the main major challenge which will come up, how we can make it more easier, user interactive to use this NAS architecture. So that will be the major challenge, so that the users can be comfortable to use this framework on their own preference, rather than having too much of understanding what is the deep architecture behind uh, the too much logic of writing the YAML script. And because people, data scientists, some of the data scientists doesn't have too much of familiarity of Kubernetes, and on top of the how to build the YAMLs and where to debug those things. I think we need to see that part to resolve the complexity on for the user friendly way.
Yeah, definitely. It's a great comment. Do you have any ideas how we can improve it from the data scientist perspective?
I think
Speaking about the NAS.
exactly. I think if you see majority of data scientists, whatever they do some Python-based environment, right? Now, if we can come up with some integrated API, like let's say we have built a simple API where they can write some sort of we'll have a defined YAML, right? And that YAML they can change the search parameter space, and on top of and we can integrate the Python on the front end, right? And on the back end the YAML scripts, and automatically it will trigger those YAML on the back end. So if we can build a SDK on top of this architecture, I think that will be great, and they can reuse it from anywhere in the Kubeflow environment. So in the
Yeah. Go ahead.
yeah, that was the thing. I mean, like a Python SDK to trigger those mechanisms, and to build the search space and all. So that was the thing.
Yeah, it's actually a good point, and we are continue working on how to actually hide this containerized Docker away from the user completely, and try to reuse the automated container build to just simply provide the parameters that you want to search or parameters that you want to tune, and then you will have the same Python environment on your Jupyter notebook. Yeah, definitely.
Exactly. Because people are using, I saw Raytune framework, weights and biases, and they're using, I mean, in my company, they're using few of the Katib, the basic Katib things, and not this advanced thing right now. Those architecture, they have to set it up. I think they need I mean, that is the gap between a MLOps and a data scientist people. So,
by the way, any ideas how architecture we should provide to the user? We probably thought about like on an X format or any other ideas that you have in mind.
yeah, actually, I was thinking few of these things, so I will get back to you. So I think we can have a separate discussion on top of that. Actually,
Mm-hmm.
maybe we can
Yeah,
tell the journey of our uh, uh, what are the challenges we faced, right? Because even I was using the Kubeflow for last 2.5 years, and what are the challenges we are facing, and to the customers and the clients. And I think we can give those things. Actually, we can have a discussion on top of that. I think Josh was.
definitely. I would strongly recommend. Can you please create an issue and we continue the discussion about like this your use cases and how should it look like?
Yeah,
What do
yeah,
you think?
sure.
Okay, thank you so much. Yeah, and the next question about like Summer, yeah, about like the integration gradients, right? Can you maybe give a quick introduction? It's like where it is used?
I can, I guess, probably easier to talk. Andrey, first of all, like great talk. Really enjoyed it. Um, so I'm kind of getting interested in a lot of areas with around explainability of the model itself. So there are two aspects. One is the interpretability, and the other is explainability. So interpretability is around, hey, like this is what the weights are. Can we like how do we visualize this, or what were the most important features? So in like some of the older classical techniques in classical ML were things like Shapley values or Lime, and in neural architectures, like integrated gradients is like one thing that's getting popular. The other one is XRI, which is similar to integrated gradients, but it basically uses like a baseline image and then like tries to like do something called as a feature attribution, like what's the attribution mask that resulted in the final prediction. So maybe I don't know if it is in context of Katib, because Katib is also like trying to get you that optimal model, and maybe the interpretability lies on like, oh, once you have the optimal model, then you apply the interpretability to it. But I saw the initial earlier slide about like the whole ML auto ML, and I feel like as we go down that path, interpretability kind of becomes important. I'm also kind of like new to these concepts, so I'm like still learning myself. But I just wanted to hear your thoughts, or if there are any plans in the working group or discussions on this as well.
Yeah, I think it's very interesting. I unfortunately we don't have like enough time to discuss it right now. I definitely agree that AutoML like space is very huge, and we can try to support this sort of the gradients there. Can we just please submit an issue as well, and we can continue our discussion in working group meetings in AutoML and training, so we can have like more particular discussion, and we will also try to go deeply in the different algorithms and how we can use it in Katib, for example.
Yeah, sounds good. We'll do.
Yeah.
Thanks.
Sounds great. Yeah, because again, we try to support other techniques like as I mentioned earlier, like model compression, feature engineering. But again, we want to start it from our user use cases, and then we can just integrate this part of the AutoML techniques in Kubeflow in general. And I think it will be very cool if we have this in open source world.
Yeah, definitely. This is like really early stages of this.
Yep.
Like, so yeah, I'm sure like we'll get to this.
Yeah.